Hi, my name is Agustin Ortiz. I'm here to present the project objectives and the client requirements. Our client will be the Tec Monterrey. Okay, for the project objectives, the mechanism is a radial cam with a rocket follower to transform the rotatory motion of the cam into a linear motion for the follower. The purpose of the design and manufacturing of the cam is to make a mechanism to drop a load. This mechanism must be done in a period of 5 weeks to be implemented into a prototype design of an AGV with a scissor lift mechanism, where the can and the entire unloading mechanism will be located. The can must provide an inclination of the rocker of 25 degrees, so the load can fall due to gravity. The measures required in order to obtain were calculated around the provided 25 degrees. Continuing with methodology, for the development of the can mechanism or the scissor lift system, we follow these steps, which ensure the achievement of the desired lifting and tilting motion. First, the initial sketches. The team began by sketching the general design of the can system, focusing on its role in tilting the discharge platform at 25 degrees. Previous calculation in image 1, which is attached in the video and PDF, indicate that the can needed to be positioned at 12.86 centimeters from the edge of the lower MDF panel, at the point where the hanger fastening the upper MDF section of the discharge mechanism is mounted, as seen in image 1.2, also attached in the PDF file. Then, we made a digital modeling and simulation. With our sketch defined, the cam profile was first designed and analyzed in MATLAB, where the displacement, velocity, and acceleration graphs were generated to value the motion behavior. The MATLAB model was then exported to SolidWorks to create a 3D CAD model of the cam. This allowed the team to visualize the interactions between the cam and the follower, check for the mechanical interference, and validate the desired lifting motion. The third part was the material selection and assembly. Then, the cam was fabricated using PLA through 3D printed, chosen for its precision, low weight, and suitability for complex geometries. The cam housing was built using MDF due to its mechanability and cost efficient. Aluminum bars and steel connectors were used to integrate the cam with the rest of the mechanism. Finally, the assembly ensures smooth rotation and reliable force transmission to lift the platform. In the fourth part, we have the testing. The cam mechanism underwent functionality testing to evaluate its ability to lift and tilt the platform as intended. Adjustments were made to improve alignment and ensure the cam profile produces the correct motion. Aquí estoy dejando un espacio porque es lo tuyo, lo del código. Y ahorita voy a empezar con la 4.1 en 3, 2, 1. Then we have the decision making and the iterations. For design decisions, we focus on the kinematic analysis, material properties, and process iterations mainly focus on optimizing the cam profile shape to achieve a smooth motion and ensure robust integration with the platform.
In the creation of the cam, there are three main processes. MATLAB coding. In this part, the main lines of code that need to be emphasized are cam.h and cam.rb. With these two lines of code, it was modified the height of each tool. In this case too, according to the height obtained from the initial sketches, that was 6 centimeters. Also, it was modified the radius of the base circle of 8 centimeters. The other lines help us to define the angular increment of each tool, where we assign a value of 240 and 2, and for the rise and fall of the angle of 59 each. Now, step number 2. After obtaining the coordinates of each point of the cam, the data was processed in Excel by multiplying each column x and y by 1000 to convert the values into millimeters. Additionally, a column of zeros was added to represent the z-axis, making the data compatible with SolidWorks. The circumference of the cam was sketched and then extruded 5 centimeters. Once the cam had volume, a hole of 8 inches was made in the center of the small radius using the hole wizard feature, so the cam will be attachable to a motor. Finally, step 3, 3D printing. For the manufacturing process of the cam, Cura software was used to slide and convert the SolidWorks file into printable format. A 15% infill with a cubic pattern was selected to reduce both printing time and weight. The part was printed using an Ender 3 version 1 printer with PLA filament provided by the team member. The total printing time was approximately 5 hours. Now, for decision making and iterations. The design processes began with evaluating multiple mechanisms considering factors such as complexity, degrees of freedom, and ease of simulation. After team discussions, the slider crank mechanism was selected for its practicality and relevance. Early simulations in MATLAB revealed inconsistencies in motion and acceleration. Prompting several iterations to refine link parameters, vector calculations, and loop closure equations. Graphical outputs like trajectory plots were crucial for identifying errors and validating system behavior. This iterative process not only improved the model's accuracy, but also deepened our understanding of the mechanism. The cam mechanism controls the lifting at 25 degrees tilting of the discharge platform in the scissor lift. Via a rotating cam, it has 2 degrees of freedom as confirmed by prior analysis. Grashof criterion does not apply since the mechanism only has 3 links while the formula requires 4. The graphs were generated using the SVAG 345 function, which applies a 345 polynomial for smooth cam motion, ensuring continuity in displacement, velocity, acceleration, and jerk. Based on a normalized input x ranging from 0 to 1, the function computes kinematic profiles refined via cubic spline interpolation. These results directly influence cam design by guiding profile shaping and ensuring low speed operation to minimize mechanical stress and ensure stability.
So now, once that we have all our points generated by the MATLAB code, we extrude them and export it to SolidWorks, and we have, as a result of that, this cam. This cam, first of all, we assign it up a material. We can see which one is, and once we have this, here's another problem. How do we make them work? So we create this ensemble in SolidWorks, and here we can see that there are two goods. These we use MDA, and with that we make some cuts through the first layer of the MDA, with the reason that we need to make it a little bit later. And with that we put our cam, and we put our two supports and an aluminum bar through the cam that it will help us to make it like work. And at the end we put two hinges right here that will help us to give the movement that we want, and as a result we have these that can help us discharge our load.
Lastly, the cam mechanism was physically realized by 3D printing the cam profile in PLA and assembling it within a precise cut in FDM housing. The cam was mounted onto an aluminum shaft, which was then supported by the MDL panels. The follower arm, connected to this discharge platform, engaged directly with the cam lobe, allowing the transfer of rotational motion into a vertical displacement. Photos of the assembly process shown the integration of the cam with the scissor lift and then successfully lifting of the platform during manual testing. Throughout the development of the cam mechanism, the team faced several challenges that require both technical analysis and practical problem solving. One of the most critical aspects was achieving the cam profile that would generate the precise 25 degrees tilt needed to unload the platform. This required multiple iterations using MATLAB, where adjustments were made to the rise and base radius until the simulated motion met the design criteria. Additionally, ensuring proper iteration between the cam and the follower demand, carefully modeling in SolidWorks to avoid mechanical interference and guarantee motion transmission. Material selection was another important consideration. PLA was selected for the cam component due to its ease 3D printing and adequate material and adequate mechanical strength for the application. MDF and aluminum were chosen for structural supports, offering a balance between cost effectiveness and maintainability. These decisions allowed the team to stay within budget while ensuring the function and integrity of the mechanism. The cam mechanism is expected to provide reliable and repeatable lifting and tilting motion, smoothly transferring rotor input into linear displacement. Its design allowed it to serve in small-scale material handling systems, automated unloading platforms, or as part of larger electromagnetical assemblies. Future improvements could include motorizing the cam rotation while with a steeper motion in order to maintain the cam up, enough time to discharge the load. Also, we could use more robust materials such as mirror cams for high load applications.